Assalamualaikum warahmatullahi wabarakatuh. And hi everyone. So we meet again to discuss about control system engineering. In the last lecture, we have discussed about how to design the controller that can improve steady state error. That is PI controller and lag compensator. So for this week, so we continue another type of controller that can be used to improve transient performance. So before we go further, let us look at learning outcomes for this topic. So at the end of this lecture, you should be able to understand how to improve transient response by designing the controller that we call PD controller, proportional derivative controller, or also known as ideal derivative composition. And second, use another technique that we call lead compensator, the same objective to improve the transient response, but the different method. Okay, what is ideal derivative compensation? So the controller that we use with this kind of method is proportional plus derivative PD controller. So in order to design this PD controller, so we have to add 0 to the forward path transfer function. So in this case, a pure differentiator is added to the forward path of the feedback control. So in order to implement this, so we have used active network circuit. While for the other method, which is lead compensator, so this kind of compensator, in order to implement, we just use passive network. That means only consists of R, L, and C component. Proportional plus derivative PD controller. So the proportional plus derivative controller produce an output which is the combination of output for proportional and derivative controller. Therefore, the equation for PD controller is G equal to KP, proportional, G is there for error, plus KD is derivative gain, D over dt of P. This is the equation that we use to implement this PD controller. The proportional derivative controller is used to improve stability of the system. So that means we want to make sure system in stable condition, and at the same time it's not affecting the steady state error. So this is same like in previous controller, PI controller, where when we design PI controller, the objective is to improve steady state performance, and at the same time we have to make sure there is no effect to the transient performance. So for this case, we want to improve transient response, and at the same time we want to make sure steady state performance still remain the same. When we talk about transient performance, so the parameter that we have to improve is TS, TP, omega n, zeta. So in order to design that controller, so we have to make sure the location of pole or can be changed to the new location that can improve the performance of the transient response. So in order to do that, we have to reshape the uncompensated root locus so that the composite new RL goes through the selected closed loop pole location. So in order to design this PD controller, so we just add 1 0 to this root locus for the uncompensated system, which is represent this transfer function TCS equal to S plus ZC. As you can see here, when we put these zeros here, so this root locus will reshape like this. So when this root locus reshape to this point, so that means the location of pole will also change to the new location. So in this case, The new location is at negative 2.437 plus minus j 5.583. So as you can see here, this location is different compared with for the system without these zeros. This is how we can improve the transient performance. In order to make it easy to understand, let us look at this example. When a plant with transfer function Gs equal to k divided by s times s plus 4 times s plus 6 is given a step input, its response shows that there is 16% overshoot. Design PD controllers so that there will be threefold reduction in its settling time Ts. Okay, so this is the transfer function for the closed loop system where the system was tested by inject step input, and then the response shows that there is 16% overshoot, and then we have to improve the performance in terms of TS and settling time without affecting the percentage of overshoot. So in order to solve this problem, so first we have to draw the root locus. And based on this transfer function, there are three poles which is located at 0, -4, and -6 with 16% overshoot. So the location of pole was moved from the original coordinate to this place. So this line is referred to zeta line, which is reflect to 16% overshoot. So the gain when this pole move to here is equal to 43.35. So you can calculate this gain by using the formula 1 over gs, where s equal to this coordinate. So this coordinate here is negative 1.205 plus minus, and because conjugate here, top and the bottom one. So that means we have two dominant poles, which is at negative 1.205 plus minus j 2.064. Okay, from this dominant pole, so the settling time we can calculate by using the formula where we already know from these dominant poles. So this part is referred to zeta omega n, and this part referred to omega d. So because this question asks find the new value for settling time, so that means we have to find the original settling time based on this location of pole. So we just apply the formula where the formula for Ts is equal to 4 divided by zeta omega n. So in this case, zeta omega n or sigma d is equal to negative 1.205. So that means we just put is 1.205 in this formula, and then we get Ts equal to 3.3196. So based on this question, we have to improve this Ts 3 times. So that means we just divide by 3. So the result become Ts compensated equal to 1.1065. Okay, that's mean in order to design this controller, so we have to make sure TS become 1.1065. To get this value, so we have to find the new value for sigma D. So based on formula TS, so we can calculate sigma D equal to 4 divided by TS compensated. So the result become 3.615. So that means in order to design this controller, so we have to make sure this zeta omega n or sigma d is at negative 3.615. And at the same time, so we have to calculate also the new value of omega d. And because when we change the value for zeta omega n, of course this value of omega d also change. From original dominant poles, the angle between sigma d and omega d is calculated by using this formula where because we want to maintain this percentage of overshoot, so that means we still use the same theta here. So theta for this case is equal to, we just use theorem particulars by taking this tangent, this value divided by this value, which is equal to 59.7335. So we just refer to the all value for omega d and sigma d. So based on that, so theta is equal to 59 9.735. To determine the imaginary part of the compensated dominant pole, so we just use the same formula, which is this formula also, but with the new value for sigma, because we already calculate sigma in this case when we improve the performance of system by using PD controller, so that sigma d become the sigma d should be 3.615. So we just put inside this formula sigma d equal to 3.615, and then theta, we use the same theta because we maintain the overshoot for the system. So that means we just put the same theta here, and then from there we can calculate omega d. So after calculate we get omega d equal to 6.195. So that means in order to improve the PS for the system without affecting the percentage of overshoot, so we have to make sure our new dominant poles, or we call it compensated dominant pole, should be at negative 3.615 plus minus J 6.195. Then after we get this dominant pole based on the requirement, so we can design the PD controller. The general transfer function for PD controller is given by this equation, where GCS equal to K2 times S plus K1 divided by K2. This equation is also same like this S plus ZC. So in order to get this GCS, first we have to assume one of the value for this K1 or K2. So in this case, we choose K2 equal to 1, and to make it easy to calculate, and because when we put this one equal to 1 and this one is equal to 1, so that means we can get the same formats like this. So we just put K2 equal to 1 for both this one and this one, and K1 become equal to ZC. Okay, we know that the contribution for angles between all zeros and poles and compensated dominant poles must be equal to negative 180 regarding to this formula. So in order to find the exact location of ZC, so first we have to find all these theta, which is referred to this new dominant pole that we designed to improve the PS. So in order to get this, we just use the general particulars. Theta 2 in this case is referred to this angle, while theta 3 and 4 is referred to this angle and this angle. So this angle is angle that refer to the ZC that we want to obtain to improve the performance. So in order to get this, so we just use this formula, because after we get all this value, we just put inside this formula, and then we can get the value for theta as minus K1. So after we substitute all the theta inside that formula, so we get the theta for ZC equal to 95.64. Okay, this is theta for ZC with respect to the dominant pole. We can plot this theta like this. So that's mean the value for zeta omega n is based on this angle is located somewhere here. So how we can know this coordinate? So we can use theorem particulars to find this by using tangent omega d divided by theta omega n here, and divided by this displacement, which is unknown. So we just put x here. So based on this formula, so we can find the value of x equal to negative 0.612. Value for zeta omega n based on the compensated dominant pole is already known, equal to negative 3.615. So based on this data, and this one, so we can find the location of ZC by subtract this current zeta omega n with this x, and then we get negative 3.003. So from here, we know that ZC is equal to negative 3.003. Based on this information, the transfer function for PD controller that we have designed is DC as equal to S plus 3.003. Now, after we get the value of ZC, we can find again the value for K1 and K2 so that we can complete this block diagram. This is a derivative component and this one is proportional component where, as I mentioned in the early discussion, the controller for PD is equal to P component plus with derivative component. And based on this, we can implement this controller to the real using this circuit by finding this value of Zn and Z2. So to find this value Z1 and Z2, we can refer to this table where for PD controller, the parallel of component C and R1 represent Z1 and components R2 represent Z2. By replace the Z1 and Z2, so our circuit for PD controller is like this. Based on this circuit, we can come out with this equation. So as you can see in this equation, so the format is same like K times S plus ZC, where the value for ZC is equal to 1 over R1 C, and value for K is negative R2 C. Now we go to the next technique, lead composition. So for lead composition, when passive network are used, a single zero cannot be produced. Rather, a compensator zero and a pole result. The advantage of this lead compensator, no additional power supply are required. And second, noise due to differentiation is reduced. But the disadvantage for this method, the additional pole does not reduce the number of branches of the root locus that cross the imaginary axis into the right half plane. So in order to design this kind of controller, so if we select the desired dominant second order poles on the S-plane, the sum of the angle from the uncomposite system poles and zeros to design point can be found. So the difference between 180 and the sum of the angles must be the angular contribution required for the compensator. An infinite number of lead compensator could be used to meet the transient response requirement. In order to design this controller, we can select either a lead compensator pole or zero and find the angular contribution at the design point of this pole and zero along with the system's open loop poles and zeros. Now let us look at this example. So in this example, we have to design lead compensator for a system with GS equal to K divided by S times S plus 6 times S plus 10. So the design objective is to improve the settling time by a factor of 2. So that means we have to reduce this TS, and at the same time, the overshoot of the system should be 20%. In order to solve this problem, first we have to find the dominant pole so that the overshoot for the system is 20%. So this can be done by obtaining the value of zeta. We just apply formula for zeta and then we just put this 20% inside this formula and then we can get the value for damping ratio zeta. In this case, we get 0.456. From this value of zeta, we can find the value for theta, where we can use formula zeta equal to cos theta. From there, we can find the theta equal to 62.87. So after we get this theta, we can draw this zeta line here based on theta equal to 62.87. Okay, the cross point between this zeta line and this root locus is the value for dominant pole. So in this case, we get the value for dominant pole is equal to S equal to negative 1.8 plus minus J 3.47. So at this point, the value for K again is equal to 190. Then from this value of dominant pole, so we can find the TS and TP for the system. So in this case, because we want to improve TS, so we just find the value of TS, where we just use formula TS equal to 4 divided by sigma. In this case, sigma value is equal to 1.8. So that means we just put 1.8 in this equation. And then we get the result become 2.22 seconds. in order to improve this setting times, we just divide this TS with 2 so that we get TS equal to 1.111. So this is the TS value that we want to get after we design the controller. So from this new value of TS, we can find again the new dominant pole after design. So from here we can calculate again the value for sigma nu. So the value for sigma nu, we can use the same formula where we calculate the TS, which is TS equal to 4 divided by sigma. From there, with the new value of TS, we can find sigma nu equal to 4 divided by 1.111, which is equal to 3.6. With the value of this new sigma, and the value of theta 62.87, so we can calculate the value for new omega d by using theorem Pythagoras. So after we calculate, we get this omega d new is equal to 7.03. So that's mean after we calculate all this, we get the compensated dominant pole for the system after we design this lead compensator become S equal to negative 3.6 plus minus J 7.03. So in order to design this lead compensator, we can choose one of zeros that can eliminate one of these pole. So in this case, we choose ZC equal to negative 6 so that this value can eliminate the pole at negative 6 and leave the system with 3 poles, same number of the uncompensated system when we put another pole to the system. And this is because for lead compensator, we have to add one pole and one zeros to the system. Okay. Based on this decision, so we just use the formula angle for theta PC. And this is a new location of pole for this compensator that we add to the system minus theta at this origin minus theta at this location. So theta for this origin we can calculate by using theorem Pythagoras. So first we just find this theta, and after that we just use 180 minus to this theta. So after calculate we get this value, this angle is equal to 117.1 degree. Next for these angles, so we just use theorem Pythagoras by using tangent. Tangent theta is equal to this length divided by this. Okay, this one is equal to 7 divided by 6 point something. So after we calculate, so we get this theta equal to 47.69. Okay, after we get these values, so based on this formula, we can get the value for compensated pole of theta. And next, from this value of theta for this compensated pole, we can find the location of this pole also using theorem Pythagoras. After we solve this, we get the location of compensated pole is at negative 29.5. So from this result, so we can conclude that the transfer function for this compensator is equal to S plus 6 divided by S plus 29.5. Okay, this is the transfer function after we combine this lead compensator and the plant. Okay, that's all for today. So hope you can understand, and please do exercise. And if you still confused, you can discuss with your friend and don't hesitate to WhatsApp me. Thank you.